So we have many collinear triples. That's the situation on the plane usually, and usually that's just the real plane. So many collinear triples. What is many? Well, it depends, we will see. And depending on the number of collinear triples, we would love to see some structure. We would like to understand how is it possible. Usually, in general, if there are many, many triples, then one would expect a strong reason why do we have so many triples. Unfortunately, we are still very far to understand what's happening there. Right, so this is the situation. Just let's see, we have many collinear triples. So we have a point set, and say we have n points. And now M will denote the number of collinear triples. Collinear triples. So first of all, if you had just one straight line with m points, then there are n choose 3 collinear triples. That's not the interesting case. Usually, when we say that m collinear triples, we really mean, well, not always, but we mean that that's the number of lines which contain at least 3 points. Okay. And now how to analyze a point set like this. So there are different tools, and depending on the tools, there are different results. Unfortunately, none of them really satisfactory. So what can we use? We will see how to use some basic graph theory. That's what we will begin with. Then that's a special subcase there, hypergraphs and the family of a powerful of problems using or answers using a powerful tool called Regularity Lemma. Lemmas for hypergraphs even. Now don't worry, those are very hard to prove theorems, but we don't have to really prove them. It's enough to state them. It's easy to state them and use them, although again, to prove them, that's a different question. In particular, the hypergraph version of the regularity lemma, that's a very advanced proof. Of course, we can use algebra in various contexts. So the general conjecture that if you have many, many collinear triples, then there is somehow a group structure behind this whole event. But yeah, that would be the nicest thing to conclude, but we can only do that in extreme cases. But you can also use linear algebra in a non-trivial way. Actually, advanced linear algebra, you can use simple linear algebra, but that won't really lead very far. And of course, for problems, incidences, arrangements of lines, of points, there are tools in algebraic geometry. And I will try to give you examples to all of those cases. Let's begin with some very simple observations. What if we have just a few collinear triples? Few still means a reasonable number. So we are at the range when c to the n to the 3/2 is about what we have for the number of collinear triples. Well, very basic graph theory would tell you that there are many C4s. If C is large enough, then about n squared C4s. That's just by the edges. And by C4, I mean C4s given by the triples. Well, this is a very big statement, and we didn't really use anything about the triples at this point. But at least this is a structure you can't avoid. And yeah, that's what we are looking for, structures which we can't avoid. Now there is immediately, if you want to use that, there are triples, a very recent and and a very advanced result of Conlon, David Conlon, Jacob Fox, Benny Sudakov, and so. And it says that if you have triangles, then you can say something much stronger than this, that either you have a triangle you know this you can really have a bipartite graph up to n squared points, so but this is not the same with triples, or you have a C4, I just run through it again, or you have C5. C5 will give us, well, the triangle, it's too good to hope for, to have a triangle. We will see that triangle is only guaranteed if we are very close, if M is very close to n squared. And even there, the proof is non-trivial. But so it would be very nice to find a triangle with such density. You can't really have that. So the statement what they proved very recently, it's not even published yet, maybe on arXiv you will find it, that if you don't have triangle and C4 and C5, then the number of edges, so if you don't have those, that implies that the number of edges is little o n to the 3/2. Yes. So for triangles, you do have here some structure, but this result, first of all, it has very interesting corollaries in number theory and in some other applications. Second, it's hard to prove. And this is not the range where we can really say much more. At least this is even more than what we expected just a few months ago. Good, so this range, maybe let's go a little further when you have, okay, still C and the 3/2 with the right constant. That's a classical result for three uniform hypergraphs. You can think that triples as edges in a hypergraph. Three uniform, that means that every edge has three vertices. Those hyper edges have three vertices. Following earlier results, one can, Bolobás, Gyuri, and Füredi, I won't really write the details here, but you can guarantee that there will be a C5. If C is larger than a certain threshold, something. Right, and as you go further, then there will be many pentagons, many C5s. So that's a result of mine with Dhruv, that actually the number, if we are between n to the 3/2, and so M is somewhere there, and let's say it's below n squared, but this bound is not that important, this lower bound is important, then the number of C5s, if you have a triple system, because otherwise, you know, for graphs, of course, you can't expect any odd cycle, but because you have triples here in this arrangement, then the number of C5s is at least larger or equal, you can still see that, M to the 6 over n over n to the n over n 7th power. Now, again, what is this? Why do we care? Well, from here, actually, you have a structure under certain conditions. So details, but here, just using this simple observation that triples will have many C5s, you can prove a theorem of Netscatz and Terry Tau, or from additive combinatorics, which says that certain, if the sum set is small under certain conditions, then there the difference can't be too large. So this is still, but it's not very useful, or I don't know how to use that for us yet, because our final goal would be to say something. So this is the range what we are really interested about. when we have about some constant times n squared triples. And that's where we will prove some kind of rigidity. Of course, you had some kind of rigidity even with a linear number of such triples, but not what we are looking for. So this is the range. Before we go, what could be the largest C here? That's a question, and that's a very old question. That was the problem of Sylvester. So Sylvester's question was that, do you have an arrangement of points where any line which defined by 2 points, there is a third one, right? Many of you know this problem. This is a very nice and old problem of Sylvester. And there are various proofs to show that no, there is always at least one line is true, which has only 2 points through the set. But that's roughly the range where we can really come up with a stronger structural result. So this structural result is due to Ben Green and Terry Tao. And they said, say, lines which have only 2 points on it, those called ordinary lines. The triple, which the lines which have at least 3 points, those are not ordinary lines. And so here is the very strong and hard to prove theorem that if the number of ordinary lines is, so m, not m, the number of ordinary lines on n point is just linear, it's some k times n, then I will just say the rough statement, then with after removing some constant number of points, constant which depends only on this k, what you're left with is a point set which lives on an elliptic curve. And on an elliptic curve, actually, you can have such an arrangement. You know, there are nice group structures of triples on elliptic curves. So just check this statement. It says that if almost all the pairs have at least 3 points, I mean, all the lines which defined by this point set have 3 points, and only a linear number of them out of n choose 2. Only linearly many are ordinary lines, then that means that there is a very strong group structure behind it. And the general conjecture, without formalizing it in a detailed and correct way, would be that whenever you have c times n squared for arbitrary small c, if n is large enough, if you have c times n squared triples, then there is some group structure, or the whole structure comes from a group. I don't go into the details, so it's a pushback. Yeah, that's not good. Right, so unfortunately we can only say such structural results if almost all the lines are not ordinary. Only a linear number of lines are ordinary. And if you have a smaller c here, then suddenly you know nothing. The question is, maybe you have 10 points on an elliptic curve, maybe. Nobody knows, so nothing. Suddenly, well, almost nothing. I can show you using a classical regularity lemma, that at least there are triangles. But even this statement is absolutely non-trivial. And in particular, what is the bound? When do you have a triangle? That's a question. That's a slight improvement on the bound. That was an annals paper of Jacob Fox. So let's see the statement, because this is a very powerful statement. Whether you are using here for triangles or for other things, you don't have to deal with epsilons and deltas as usually with graph regularity. It's a simplified version, it's a corollary, and we don't have to prove, but here is the statement. So the statement is relatively simple. It's about graphs. Let's just state first, not hypergraphs, just graphs. If a graph Gn, so this is a graph on n vertices, it has the property that every edge in this graph, every edge is the edge of exactly one triangle, then the graph Gn is sparse. Sparse means that the number of edges is little n squared. So not constant times n squared, that would be dense. Well, let's see this condition. What is this? This is just a graph. You begin to draw a graph. Here is a graph. There is an edge. Then there should be one triangle, but not two. Then you can't really add a triangle here. Then you draw another one. If you begin to draw it without allowing any extra triangle, then as you draw it, it will be a pretty sparse graph. Yeah, you can't really draw a very dense graph. But to prove it, now that's regularity lemma. That's hard to prove. Just to illustrate the difficulty of this statement, that this is a simple statement on graphs, but this implies, this very simple statement here implies Roth theorem. Which is about the three-term arithmetic progressions, that if you have a dense subset of the first n integers, so C dense, if you have just Cn numbers out of the first n, then somewhere there will be a three-term arithmetic progression. And there are constructions, balance construction, a beautiful geometric construction, which will show you that there are point sets which are almost size n, where you won't see three-term arithmetic progression. So this very simple sounding statement that if you have a graph where every edge is the edge of exactly one triangle, that's a powerful theorem, very powerful. And how to use that? So let's go back. We have triples now as a geometric problem. Yes. Every triple is now just extended to a triangle, a small triangle, little deviation from the linearity, but for every triple you have exactly one triangle, yes? And every edge in this, every edge in those skinny triangles is just the edge of exactly that triangle, the skinny triangle. So using this, either the number of such triangles is less than n squared, or we will see a triangle like this one here. This is a triangle. Here is the triangle, and those are the remaining vertices. So this is a small structure, but at least you can have that. And there are further conjectures locally. How does it look like? The only thing we can say after using this really powerful result is that there will be triangles. So if M is about C times N squared and N is large enough, in terms of C, then there are 3 collinear triples forming this configuration. Right. So that's a very local structure. The hope is that maybe you can glue them together and you can continue this to build the structure from local properties to get some larger results. There is a very recent paper of David Conlon, and they continue this line, but we are still very far from structure. Right, that's already 20 minutes, so I will skip the complex case. That's interesting. That's a part where it's a book work comes, that's serious algebraic geometry, but for us, maybe that's not that important. Let's see, so rigidity. Let's immediately, I jump now, I leave some parts here, which I wanted to talk about. Maybe before I leave this part, the regularity lemma, this is one way to state the regularity lemma. It was a simple statement, yes? Again, it's a very powerful but simple statement, simple to state. If a graph is exactly one triangle, then the graph is sparse. And there is a hypergraph along. Let me just say for triples, but one can state it for arbitrary hypergraphs. So for triples, that would be well, so that's a 3 uniform hypergraph. When you say that, then you think of triples, not in triples like here, but in a set theoretical sense. If you have n vertices, then the maximum number of edges is n-3. That would be the complete graph there. 3 uniform hypergraph on n vertices. And if it has the property that every edge is the edge of exactly one click. So here we had an edge and we had a triangle. A click from here is 4 vertices where all triples are edges. So like a complete subgraph of one click, then it is sparse. And instead of R uniform, you can write here, instead of 3 uniform, you can write here R uniform, it works. And this very simple statement, what we have here, if you digest it, so again, the click means that you have 3 plus 1, or in general, R plus 1 vertices, and they're all possible edges. Like for the triangle, you have 2 plus 1, that's 3, and all 3 edges. So for hypergraphs, this statement here can prove you the full, even the multidimensional Semmelweis theorem, which is a very advanced theorem, which is a generalization of root theorem about k-term arithmetic progressions. So this quite far, this statement. If you are interested about it, then for applications, you will see some of my papers on that. But we are interested about rigidity mainly. Okay, so what do we want? What we want is that when you have an arrangement, many triples, so again, we are at the range when M, the number of triples is about C times N squared. Then we think that somehow we can control this whole arrangement. And in general, well, okay, let's see just let's just stay with triples as it is now. So what does it mean to control it? Well, it would be nice to say that many points are on a low degree curve. So if we had a statement that many of the points will live on a low degree curve, so you had many more points and the degree, fix a few points here, then the remaining points should stay on the curve. So that's some kind of rigidity. But what we really did, so this is a joint work. What I will just briefly mention here. It's a joint work with Zev Dvir and Anit Garg and Rafael Oliveira, that the details here, that if m is about c times n squared, then one can choose some k which depends only on c points, it's a constant, out of the n, such that after fixing them, you pin them down. After fixing them, the system is, the triple system is rigid. Okay, what does it mean? It means that if you have to keep all the incidences, if this triple was here and the other one was here, so wherever they meet, if you have this list that through this point you have those triples and the other points you have those triples, so you think those points as, I don't know what is the right terminology in rigidity theory, so you keep the incidences, but they can rotate. So if you have two, then they can rotate. Of course, this angle is not fixed, and also they can move up and down. So all what you fix is just that this point is the meeting point of those triples. You don't fix their length, don't fix anything, just the incidence structure. Okay. And then you need just a constant number of points that if you stab your picture there and you say, again, the triples are not rigid, those are not bars, those are just saying that they are collinear. So just keeping the collinearity condition and the incidence structure, your system is rigid. Any questions at this point? So this is one way to understand the structure. Saying that, it really says that you can describe the whole system with a degree k.
Do you mean locally rigid or globally rigid?
It's globally rigid.
Okay.
I wasn't really careful here saying that we have some conditions. So there are cases when they flip. So right. Maybe I can say that every point has a small neighborhood where no other point can be found. But it's rigid. So rigid after fixing the point. If you have a system of incidences, point line incidences, then without fixing some points, there are always all those line preserving transformations which will keep the incidences. So it's a bit more than just the Euclidean motions. Here you have all the projective transformations which will keep the incidence. But if you fix a few points, if you stab them, then that's it. you can't move them anymore. So in the remaining few minutes, I will talk about this proof. The key to the proof comes from, or the inspiration comes from an earlier work of Barak, Dwyer, Wiggers, maybe a new page is. So there is a work which called fractional Sylvester Gallai, fractional. So Sylvester Gallai, you know, that was the Sylvester's problem that I said about ordinary lines, and Gallai was one of the, not the first one, but independently one who proved the theorem. Sylvester, this is the Gallai theorem or theorems. I write here the title because this is a Proceedings of National Academy of Sciences paper, and it's non-experts even. So if you want to review what we are going to see here, that's a very good point to start. And the key will be, so the key will be to deal with matrices. And many of you know matrices much better than I do. In particular, we have to find the rank of, or find out or bound the rank of certain matrices, and that will give us the result what we are looking for. You know from rigidity that if you write the rigidity matrix and you know the rank, then you know that it should be full rank minus, well, depends what are the Euclidean transformations there, and then it's rigid. I hope I said it correctly. Robert, please correct me if I say something stupid. But again, the rank of the matrices, that's a crucial step here. And for that, I will define a special, or they define a special family of matrices. So maybe I should, so you will find this paper. This is a short, nice, easy to read paper. It's a paper of Barak, Boaz Barak, then Dwyer. Oops. And Wiggers, Avi, and Amir Yehudanov. Yeah. Right. So what we will need is design matrices, is the notion. They called it, but maybe over. So design matrices. So when you work with rigidity matrices, then usually the number of rows, that's the number of bars in a bar joint framework. That's not much larger than the number of joints. At least I think that's the case. Maybe there are other cases, but in this case, for us, we have pretty much. So this is the matrix what we are going to talk about, and in every row, like with the rigidity matrix, in every row you represent a bar, and then you know the condition that this bar is rigid. It's just here you can represent somehow I just write 3 potatoes here, the fact that 3 points are collinear. You know, 3 points are collinear, you can express it algebraically relatively nicely. So that's what we are going to use here, but first the definition of the design matrices. So the design matrices have 3 parameters for the simplest case, and we really apply to our result for collinear triples, then it has more. But say, let me just illustrate the method. Q, K, and T, that's the 3 parameters we are going to use. Design matrix that has the following property. So it's an m by n matrix. It has n columns here, and n columns and m rows. And what typically it does is the following, that a typical row has many elements, okay, and a typical column has many elements, a typical row has few elements, so I just write here many, and I will quantitate it in a minute. And here, so many elements and few elements. And there is one even more important condition for the three numbers, for the three parameters. We will see what are those, that if you see two columns, then the number of common non-zero entries is small. So in the definition of design matrices, I really care about the zero non-zero patterns only. Okay, I didn't say what are the values what I'm going to write there, and it's indifferent at this point, right? So there are some zero entries, and wherever you have a non-zero entry, now you can write one now for the easy counting, for the calculation. So your original matrix is not a 0-1 matrix, but in order to we use 0 and 1. Okay, so what are the parameters? The parameters is that in every row, you don't have more than q, so qkt. Q smaller or equal than q entries, non-zero entries. Okay, in every column, you have at least, what was this number, k? Okay, at least k non-zero entries in every column. And here is this other parameter, which you can say that if you have here the indices, which are not zero, then the intersection of the two, or the number where in both you have non-zero entries, this number is smaller or equal than t. So this is the third parameter. Now, you worked with joint bar matrices a lot, I think, almost all of you. So you know that in a typical row, you have 2 or 4, depends how do you write the coordinates. Normally, I think like 4 non-zero entries. Everything else is 0. So this is like this. And you know that if you have 2 columns, that's like 2 vertices, then maybe you have 1 bar in between, but you don't have many bars in between. So that's what is, it actually, in your case, that would be 1 here. Yes? Yes. And what is not a typical, or I think it's not a typical case in when you work with the matrices, is that here you have many entries here. But for us, you know, we have many collinear triples. That's what we started with. So there are c times n squared rows, and in every row you add 1. Every row you have 3 times 2 or something like that parameters, not more. But you have c times n squared lines, so you have to fill the columns typically. Right. This is the definition. Is it clear what is a QKT design matrix? A QKT design matrix has 3 parameters, and the 3 parameters are: no row contains more than q non-zero entries. Every no row, yes, every column has at least k entries. And if you see any pair of columns, you don't have more than t positions where both are non-zero. Okay. Now, I would say that such design matrices have high rank. And that's indeed the case, but it's hard to prove and how to get good bounds. And the real difficulty is when, instead of just single entries, like in our application, in our paper, you have matrix entries, and you have to. But let's leave it out. It's a technical detail. You can follow that, or you can do that later. For a second, let us suppose that we have a design matrix where every entry is really 0, 1. It's not a requirement. So design matrices can have any entry, right? Any non-zero entry. We just were careful to record the non-zero entries in the matrix. It could be even complex entry anywhere. So, but let us suppose for a second that we have a 0, 1 matrix. Do you see why this matrix has high rank? So there's a simple way to check that. Namely, you know that if you multiply it with its transpose, then that's and this is the transpose. Let's say those are just real entries now. That the rank will be the same. Yes, we didn't change the rank with this matrix multiplication. But what will be the product? You see, if you check the product, which I write here, where will you have large entries? The only position where you have large entries are the diagonals, right? Because here you have many entries. Of course, if you multiply it with itself, with the same row, then you will find all k elements there. So here you have a large number, larger or equal than k, if you assume that this is a 0, 1 matrix, right? Right. So if you have another, you know, between those two, here it comes, this condition. The common entries is only t, not more. So when you do the multiplication, everywhere else is maybe t, which is a small number. So you have here a matrix where the entries in the diagonal, well, if it was just a 0, 1 matrix, are pretty large. And it's similar to something which is like a diagonal dominant matrix. And then you can find good bounds on that. The crudest, or I don't know, the harshest way to bound the rank would be like Gershgorin circle theorem, but you don't need that. Let me, at this point, let me advertise a paper of Noga Alon, which, if you are interested about, and you should, about ranks and tricks with that, I will continue the design matrices in a minute. This is a very short detour advertisement of Noga Alon, but this is an important paper. And the title is somewhat strange, but perturbed identity matrices have high rank. All of us have, is a beautiful approach, high rank proofs, and it's also part of the title. So I can recommend this one. Right. But if there are no questions, then let me go back to design matrices. There were we. I think we agree to this hand waving that if you have those properties, if k is large, t is small, q is also small, then the rank is pretty large. But unfortunately, when we work with design, this situation. So what can we do? Well, what we do is a little bit of cheating, I think, or I don't know if it's cheating or not. We will modify the matrix as much as we can to make it similar to a 0, 1 matrix, at least through the calculation. And then apply the relatively easy diagonal dominant calculation. And it goes back quite a while. In 64, Sinkhorn proved a very nice theorem. Well, this is about m by m matrices, but you know, for the asymmetry, if you multiply with the transpose, you arrive to this point. But you can do that with arbitrary matrices. But what Sinkhorn proved is the following, that if you have an n by n everywhere positive entry matrix, so everywhere positive, right? Then you can find two diagonal matrices, D1, with all entries here in the diagonal are larger than 0, so positive, right? D1, if this was A, then D1 times A, and another diagonal matrix, D2, with positive entries in the diagonal, with positive entries and 0 otherwise. So then this one is doubly stochastic. That means that for every row, the sum of the entries is 1, and for every columns, it's doubly stochastic. The sum is 1. So in the previous example, I said, or when we defined the design matrix, that it would be beautiful if all entries would be 1, but that's not the matrix which really represents the situation what we have. We have coordinates or linear dependence of the 3 points showing that they are collinear. So there are arbitrary numbers. Yes, but this technique, actually those matrices are almost unique. So of course, if you multiply this one, then you can divide that one, but that doesn't matter. So the technique from here can be used to make our matrices, the design matrices, close to, well, I can't say that every entry is 1 individually, but when you do the calculations, then they behave similar to the 0, 1 matrices. And then that's a rank bound. So let me write here the rank bound what we have for design matrices. So if you remember, we had, what were the parameters? We had Q, K, and T design matrix. It was M by N, and this is A. And then the rank of A, so this bound comes from this early paper I mentioned in the Proceedings of National Academy of Sciences, but we improved and find it for other cases. So this is a very nice bound. N, well, it won't be larger than N, minus Q times T times N over 2K. Well, here, unfortunately, we have a square. But as I said, this is not the sharpest, but this is what from their paper. Let's see what is this. It says that would be the full rank, yes. And now you remember this? So what was Q? Q was the number of entries in a row, not too many. So this was Q. Then we had K, right? Well, that's large, but not larger than M, anyways. So we have T, that was just, so K being large, that's actually good, because then this thing will be smaller. Q being small is good, yes? The common entries for a rigidity matrix T would be 1 or something like that. And well, N is here, but we divide it with K, and Q was the parameter. So Q is about a constant, T is about a constant, and we have N squared over 2K. But typically in our application, K is close to N squared. Yeah. So this is pretty close to N. It's pretty close to full rank. This thing here will be a design matrices. And now it's 20 past, even more a little. So soon I have to leave, but this is I think a very useful information with the references. If you didn't know that just yet, whenever you work with matrix rank, and I think many of you will, and many of you have to work with such things, this is a very useful tool. And it's very combinatorial. And yeah, so maybe the reference to our paper is so this is Dwyer, Garg, Oliveira, and myself, and rank bounds for design matrices. For us, we needed, I didn't go into the details, there's no time, with block entries. And geometric applications, there are others. Right. Okay, so that was the presentation where I did show a very powerful a little bit of. I wanted to emphasize that that very powerful tool can be used based on this very simple text, and then we went to rank bounds, which, as I said several times, and as I expect many of you use several times. Tony, are you here?
Thanks, Joseph. So are there any questions for Joseph? I guess you have 2 or 3 minutes to answer a quick question if there is one.
Well, I have 5-10 minutes, of course.
So I guess you really were working with rigidity and not global rigidity. Is there a reason they're the same for these triples?
So my goal, yeah, you know, I'm not from rigidity world, and my goal was to somehow understand what is the degree of freedom if I fix the incidence structure. Mm-hmm. So that's for me, that's the important question. And I don't know global or local or general rigidity. It's not clear, so I didn't talk about the general point line incidence question, just about this very small window when I see many collinear triples. But of course, this goes for the general point line incidence bound when you are close to the Samari-Trotter bound. Yeah. So even if this is not your area for many of you, this incidence bound and neighborhood, I think that somehow, if nothing else, the tools, I'm pretty sure I just said several times that you had to deal with various matrices and matroids also, if you had that, right?